All right, let's go through this. We have a cart made of a block of mass m. The cart's released from resting rules without slipping onto the top of an inclined plane, from the top of an inclined plane of height h. Now the nice thing about energy problems is you can set wherever you want to be ground level, h equals 0. It's most convenient for our situation to call this height here h equals 0. What does that do for our problem? Well, when we get down to the bottom, what happens to the potential energy? It's 0. So when we set up our equation, the potential energy at the bottom is going to be 0. It also says released from rest. What does that mean? Kinetic at the top is 0. So clearly we're starting here, and for the first part of the problem, we're determining this when it reaches the bottom of the incline. So that's when our physics, we want to stop our problem. So we start at the top and go down to the bottom. Now the rest of this stuff is not consequential for us. It may be later in the problem, but for this part, we're starting at the top and we're finishing at the bottom. So those are our points of interest. The energy it has on the top, it could have gravitational, it could have kinetic, it could also have spring potential. At the bottom, it could have gravitational, it could have kinetic, and it could also have spring potential. It can have all these things. Does it have gravitational? At the top it does. Does it have kinetic? At the top, does it have a spring at the top? No. When those things go to 0, what we're left with is mgh at the top. Does it have gravitational potential at the bottom? Not if we call the height 0. That's 0. Does it have kinetic at the bottom? Yes. Does it have a spring potential at the bottom? Not yet. But remember, there's where we're finishing our problem. Yeah, there's a spring, but later on. So this is what we end up with as our equation. Out of all these potential energies, we ended up with just those two. Mass divides. Root 2g. 2, gravity is a constant, h is given in the problem, we're good. So that's the velocity at the bottom of the incline. For part 2 of the question, part B, it rolls down the incline, now it goes against the horizontal surface, and it collides with a bumper. That bumper doesn't have any mass, and it's connected to a spring which has a constant k. Determine the distance the spring is compressed before the cart and bumper come to rest. So now we're starting when we get to the bottom of the incline, and we're finishing our problem when? When it strikes the bumper? When it's fully compressed. So this bumper is going to be compressed some distance x. And when it's fully compressed, that's when we're going to stop our problem. So now we go through our energies again. You could have this, spring when we start. You can have this, and this when you finish. Which ones do we actually have? Gravitational potential? No, we're on the ground. We call that height equals 0. Kinetic? Yes, because we're moving. Spring potential? Not yet. Gravitational potential? Still no. Kinetic? No, because when that thing is fully compressed, the velocity goes to 0. If it still had velocity, it would still be compressing it. So when the spring is all the way compressed, the velocity goes to 0. Do we have spring potential at the bottom? We do. And spring potential energy is 1/2 kx squared. So to determine that distance, solving for x, divide through by 1/2, the x all by itself. X max. mv squared divided by k. 2 mgh over k. suppose that instead of starting the problem here, we started it here. Energy is conserved, there's no friction, so we should still be able to do this. What type of energy does it have at number 1 now? It has potential, and that's it. It's going to roll down, and then at the end, it's only going to have potential. So we've converted all the gravitational energy and put it into the spring, which is fine because this is all the energy we started with anyway. We never had more energy than that. 2 mgh over k root equals x. That's good too. So, what do we say? Velocity must be equal to 2gh. So velocity is root 2gh. Comparing this guy to this guy. Sure was. Good deal. Yep. All comes back. So multiple ways of solving energy equations. And either one of those is logical, and either one of those works out. For part C, it asks something about it only goes 90% of the compression. What do you think that is? Friction. If there weren't any friction, what else? Heat? 90% is pushing it. 10% of the energy probably didn't go into heat or sound. Into the wall? No, I think it still would go into the spring first. Probably to turn the wheels. That's a C topic, but rotational inertia. It takes energy in order to spin something. So if those wheels are going to turn, then it's going to take energy to turn them. Normally in these types of problems, you end up sliding down to eliminate that as a factor. But since this has wheels, I guess you could call it that. Friction is the obvious answer.